Okay, we're going to go through an example of how to resolve a weight force into x and y components for an object that is sitting on a ramp. So in this example I have a 20-degree slope angle. So here's my ramp, and the incline angle is 20 degrees. I have a box sitting on the ramp, and I have the weight force drawn coming off of the box going straight down. And the first thing we should probably do is figure out what the weight is. The mass is 2 kilograms. Weight is mg, 2 times 9.8. So my weight force is going to be 19.6 newtons. So what we want to do in this example is we want to resolve the weight force so that part of it points along the ramp and part of it points down into the ramp. We do that by drawing a right triangle. The reason why we do this is we want to know what this normal force is. That normal force is going to be what we use to calculate friction, which is going to oppose the sliding down the slope. So your right triangle is going to look like this. Remember that the original force is always the hypotenuse of the right triangle. If we break it up and resolve it into components, we can't have components that are larger than the original force. So that'll help you remember that the hypotenuse is the original force, and my right triangle is kind of tilted like this. And what it allows us to do really is kind of turn our heads so that our x and y coordinates match the slope of the ramp, so to speak. And the angle at the top of this right triangle is the same as the angle of the ramp if you draw it in this way. So what we have here is the sine of 20 times the hypotenuse will give us the opposite leg, and the cosine of 20 times the hypotenuse will give us the adjacent leg of the triangle, or my weight force in the y dimension, or my weight force in the x dimension. So those values are as follows. The y component is 18.4 and the x component is 6.7. Now check yourself to see if this makes sense, because most of my weight force is in the y dimension, which is kind of pushing into the ramp. Some of the weight force is wanting to kind of pull it down the ramp in the x dimension. That's what this guy up here. That makes sense because my angle is relatively small. As my angle approaches, let's say 45 degrees, well, we should have equal weight in the x dimension and weight in the y dimension. And as we get really steep, my weight force down the slope is going to start to exceed the weight force in the y dimension into the ramp, so that friction will become less and less the steeper that the ramp is tilted. So here's the force diagram for the forces acting on this block. We have the weight force in the x dimension, the weight force in the y. So now we can write these values in. 6.7 down the ramp, 18.4 into the ramp. And the key is that the normal force is going to equal the weight force in the y dimension. So I know that this also has to be 18.4 newtons. I'm also showing a frictional force here, which if this block is just sitting there and not moving, that frictional force would equal 6.7. It would equal the weight force in the x dimension. Friction's holding it from sliding down the ramp. So this explains why we can't just use the weight of an object to calculate friction. The weight of the object, 19.6 newtons, is a lot more than the weight force in the y dimension. So because we're on a slope, there's not as much pressure between the block and the ramp, therefore decreasing the frictional force. So this case I have drawn here is an equilibrium. But let's say that friction is all of a sudden reduced to nothing. In that case, this force goes away now, and we're going to have a net force, aren't we? we're going to have a net force down the ramp of 6.7 newtons. And what might be the acceleration of that block now at this point? Well, the weight force and the y dimension and the normal force are balancing forces. They're not going to be involved in any sort of net force. So my net force, we just set this 6.7 equal to second law, and we know the mass from earlier is 2 kilograms, and we can solve for the acceleration down the slope, 3.3 meters per second squared. So this is a really critical thing to understand. I'm going to revisit it one more time. Is this how to create from a weight force of an object on a slope, to create that triangle where my weight force goes into the ramp and my weight force goes down the ramp. And if you draw that triangle correctly, keeping the hypotenuse as the original force, and put your angle up here from the slope angle, you should have no problems with this. Okay. Goodbye, everybody.